Okay, continuing on. Mendel's procedure. What did he do? Well, he studied pea plants, and he was kind of lucky in the fact that he chose pea plants because they're genetically really very simple and that they only have two versions for every trait. They're not like us, like we have 5 or 6 different colors of eyes and heaven knows how many different colors of hair and skin tone and all of those things. Peas, relatively simple. Flowers are purple or white. They're either tall or they're short. They either have yellow seeds or green seeds. So just two versions of everything, two alleles. They were really pretty simple. Had he chosen something a little more complex, he probably would not have discovered what he did. So in growing his peas, he was going to take, first of all, purebred plants. Now, when he went to get his seeds, you can go to wherever you go to get the seeds and say, listen, I want seeds that are just going to give me red flowers, and they have those. Or you just want white flowers, and they have those. So he got pure plants, meaning that for whatever trait he was looking at, he was sure he was always going to get that trait from those seeds. So he grew some plants from these pure seeds. And let's say he was looking at plant height. Plants were either tall or they were short. So he cross-pollinated a tall plant with a short plant. And the mechanism for that transfer is described in your book, and you do need to read about that. So we're looking at the plant height. We have tall, we have short. So a pure cross would be big T, big T. One big T from mom, one big T from dad, crossed with a short plant, which would be little t, little t. One small t from each parent. Why 2 letters for each of these plants? Because they got one from each of their parents. Every plant will pass on one allele to their offspring, and they can pass on either this one or that one. So the resulting plants from this cross were all tall. Now if you cross a tall plant with a short plant, and you don't know anything at all about genetics, and you don't know anything at all about DNA, you're going to wonder, where in heaven's name did short go? What happened? Okay, so he figured out that the only way to figure out where short went was to allow these plants to self-pollinate. Don't do any maneuvering with the pollen and everything. Just let things happen naturally. And he let these, the F1 plants, which means first filial, comes from the French word for son, so the first son. So those first plants that he grew, he allowed them to self-pollinate. And the plants that result are called the F2 generation, or the second filial generation. And to his surprise, short showed up again. There were 3 times as many tall as there were short, but sure enough, short showed up, so it didn't disappear. It didn't go away, and he figured out it must have been hidden. It must have been overpowered. And it was this observation that led him to his theory of dominance, that one trait is dominant over another trait if they are mixed together. So this dominance was one of his major laws that we still use today, even though we've found that not everything is purely dominant over everything else. And because we're looking at one trait and we're creating one hybrid, this is called a monohybrid cross. So we're observing the inheritance patterns and being able to predict what will happen if you cross 2 plants observing one trait. So I know you've done Punnett Squares, most of you, but if you haven't, we will go through these pretty simply and pretty quickly. A Punnett Square is named after Reginald Punnett, and it is not used to tell us, you see four squares down there, that if we cross 2 pea plants that there will be 4 offspring. That's not what's being stated. what's being stated is there are 4 possible combinations of their alleles. And so there are 4 possible outcomes. So a Punnett square is used to predict probability. And if you fill this in, you're following Mendel's procedure exactly. We're going to cross a tall plant with a short plant. So we're going to take the genotype of the tall plant, big T, and the genotype of the purebred short plant will be little t. So we would say that both parents are homozygous for their traits. Big T, homozygous dominant, little t, homozygous recessive. So you put the alleles for one parent across the top. We're only going to pass on. Now that big T individual is only giving one T to its offspring. So it could either give the left big T or it could give the right big T. Same thing for the short parent. They're going to pass on either the first T or the second one. And then you put them together in the box, you go down and across, and you see that all of the offspring are big T, little t, and they were all tall. Short's still there, you can see it, but you can't see it when you look at the plants. So the F1 generation, those are the ones that are in the 4 boxes. They are all big T, little t, they're all tall, and we would say they are heterozygous. So what he did next was he crossed those F1 plants, so the big T, little t plants, because he didn't know what happened to short. Where did it go? So that he allowed them to self-pollinate, and then he observed the traits from the plants that he grew from the seeds. And so you take a big T, little t plant, cross it with another big T, little t plant, and in the boxes are your results. You get some that are homozygous dominant, 2 that are heterozygous, and 1 that is homozygous recessive. But 3 out of the 4, when you look at them, their phenotype will be tall. So I told you there were 7,324 seeds that he observed. Of those, 5,474 were tall, 1,850 were short. And even though it isn't exactly a 3-to-1 ratio, it's close enough that we would say it's a 3-to-1 ratio. So this is the first steps in moving to figuring out just exactly how traits are passed from parents to offspring.